I will talk to you about stem cell and gene therapy for cystinosis and how we reach, even the point of even talking about it. So, I'm not sure it works. Okay. So, Corinne did a really great introduction on the genetic part of cystinosis, and so now it will be very easy for me. So, you understood that the gene involved in cystinosis, just trying to find that. The gene involved in cystinosis is called CTNS. It encodes a 7 transmembrane domain protein called cystinosin that allows the exit of cysteine out of the lysosome. So that goes to your question. This is the main player, because when the cysteine, normally exits the lysosome, it's reduced in cysteine and reused for other protein. In the case of cystinosis, there is mutation in the gene CTNS, so there is no longer functional cystinosin. So the cysteine stays stuck in the lysosome, produces cysteine crystals that everybody knows, in all the tissue, and lead to a multisystemic disease. Because the major problem of this disease is that CTNS is expressed in all the cells of your body, every single cell. So that's why Corinne was talking about the problem of producing this protein. There is a lot of disease where only one tissue of your body is touched, and in this case it's much easier to do a targeted therapy for one tissue. But in the case of cystinosis, the major problem is that every cell misses the protein. So it's where the therapy is more difficult. So what is the treatment today? You know better than me, what is the treatment, and it's called cysteamine. It allows the exit of the cysteine out of the lysosome. But you know even better than me what are the side effects of this treatment. And plus, this doesn't prevent the kidney transplantation. There is no effect on the proximal tubulopathy. But also, we realize that this also only delays the symptoms. It's not a cure. Finally, I think it's because the cysteine doesn't completely exit lysosome. So it's only, slow down the disease, but, finally they develop the symptoms. And why I'm talking about that now, it's because, Betty will tell you about the registry, but I just wanted to insist on that. Nancy and with other players, they created the Cure Cystinosis International Registry. And I think it's really important that you understand and that you spread the word to all the families that they have to register. Nobody will benefit from that except you, because what we are facing now with new therapy, what we hear from other people who don't know too much the disease is that there is already a treatment. So there is nothing else to do. So we are facing, now people saying, no, you can't do gene therapy because, there is already cysteamine. So that's why, Nancy and others decided to create this registry to show these people that it's not true. So, you have to register. So this is, how you can help us. This is what you can do. Because, now, today, there is 250 patients, and I heard that it's even growing every day. And this shows that 89% of these patients started cysteamine before 5 years old, but still 30% of them had a kidney transplant and 77 before the age of 16 years old. And that almost 50% of them still experience muscle weakness. So this shows that cysteamine is not a perfect treatment. This is just an example of all the answers that, and all we can get from it. But from our part, I used this registry several times for, the protocol that I will talk to you later. So it's a very important tool for us. There is the European registry that Corinne talked, so that will be also very important. But this is more the physician who do that. This one, it's you who can register anytime you want. Alright, so what are the different strategies when you face a lysosomal storage disorder like cystinosis? So you have an enzyme replacement therapy, and this was your question. Why don't we synthesize cystinosin? And I think already Corinne answered this question really well, because there is some disease for which this is possible and works perfectly well, but because cystinosin is a transmembrane protein, it's more difficult. So, I mean, I know that Justine is working on that, but you know, for now it's not an option. There is a supportive therapy, you know, to treat every symptoms, you know, individually, and it's that's why you have, you know, so many pills, and so that's what is done. The substrate reduction therapy. So this is what cysteamine does, you know, because it's exactly what's going on for cystinosis. You avoid the accumulation of a product B. But you see in all these cases that you are acting downstream of the problem, you know. What we want to do is to act at the origin of the problem, the gene. And you realize the difference of that is that if you succeed, this is a long-term treatment. So, as I said, the problem of cystinosis is that we have to correct every cell of your body. And there is no way of delivering a new gene or correct a new gene in every cell of the body. This doesn't exist yet. You know, we are not there. So when we started this project, you know, I was thinking, what can do the job? What vehicle can we use to bring the gene everywhere? So the only vehicle that we can use right now and could do the job is what we call the adult bone marrow stem cells. So what are the stem cells? Stem cells are so cells that reside in your bone marrow. So in every single child, every single adult, you have stem cells. And what they usually do, what are their role, is that they migrate to any injury in your body to repair it. So if you have an injury, they will, you know, they get mobilized in the blood and go to the tissue and repair it. And they can do that in every single organ. So that looks good, right? Because, you know, every you know, it's a multisystemic disease, every tissue is touched, so, you know, why not? It seems simple, yeah. So and I want you to understand that what I'm not talking about, just, you know, this is just an apartheid, but I'm not talking about IPS, you know, the new embryonic stem cells, you know, the one that are, you know, controversial, you know, ethical, and because they are not even possible to use in humans, you know. So on the adult bone marrow stem cells, because there is no controversy on that, there is no ethical problem, and they are already in use in a lot, you know, in clinical, and for years, you know, for decades, because if you have leukemia, for example, they do a bone marrow transplant. So there is no controversy on that. So, you know, because sometimes I get this question, you know, there is no, I'm not talking about embryonic stem cells. So, the most common used stem cells is called hematopoietic stem cells. I won't go in the details, you know, what they are especially, but, you know, just for you to know, this is what we will call HSC for this talk, hematopoietic stem cells. And maybe what you will, we call them also CD34 hematopoietic stem cells, just for you to know, because you will probably hear that a lot, you know, in clinic or, you know, by physician. And the good thing about this stem cell is that we can easily mobilize them from your blood. So what they do is that they give you a drug to increase the number of stem cells in your blood, draw your blood, and that's it, and we get your stem cell, as easy as that. And the good thing about these stem cells is that we can also genetically modify them pretty easily. I will show you. That was the idea. So now we have to prove the idea. You know, as any genetic disease, what you have to do is what we call the preclinical studies, which consist of using an animal model of the disease, and, you know, test your therapy first. So it's what we did. So we used the mouse model of cystinosis that was done in Corinne's lab. And the good thing about this mice is that they accumulate cystine in all the cells of the body, get cystine crystals, like the human, and they replicate the disease pretty well. So they have bone deformity, ocular anomalies with corneal cystine crystals, muscular anomalies, neurological defect, and they have the renal dysfunction. So they start to have the renal dysfunction around 6 months of age, and by the time they reach 15 months of age, they are going to end-stage renal failure. So I mean, it's a really good model. We are very lucky to to be able to replicate the disease so well. So what did we do? We isolate the bone marrow stem cells, or the HSC, from a donor mice, which is what we call a GFP transgenic mice. So basically these mice are green, and they express a normal Cystinosis gene. Because before going into genetically to do any genetic modification, but first you want to know if this has a chance to work, So what we did first is to test the cells that express already the gene, so no genetic modification, but plus these mice express a green gene. So you can follow the cells after you transplant them. You okay with that? So, and as control, we use cells from mice that are cystinotic to make sure that, if we see a benefit, it's really because there is a new gene there. So we took the bone marrow stem cells, we isolate the HSC, and we transplant just by a tail vein injection. So it's like, we just go to the vein and just do a simple injection of the cells into the mice, of the cystinotic mice. And before doing the injection, we have to irradiate the mice. And why do we do that? It's important to understand because it's the same principle in human. We have to irradiate the mice to remove their own stem cells. Because if you don't make space in the bone marrow, your new cells won't engraft. So it's the same principle in human. We have first to remove your bone marrow stem cells to put the new ones. And after we analyze them. So the first thing I did is I went to what we call a confocal microscope, so it's just a microscope, and I went and looked at the kidney because, I was coming from, Corinne's lab, so she's a nephrologist, and we were very interested in the kidney. I was thinking, because you understand that we have to correct every cell of the body, I was thinking that, if I see just a couple of cells, there is no way this treatment will ever work. So I was hoping to see, like at least 10% of cells, something, So I wanted, that's why the first thing I did is to take a kidney section, go to a microscope and see what we see, And what I was expecting is to see green cells, because the green cells were the cells that were coming from the cells that I transplanted, who carried the Cystinosis gene and the green fluorescent protein. So this is the control. I showed the control because last time, he's not here, but he asked for the control, so I put it today. So this is the control. I thought that I could, skip that, but no. So this is the control. So from a mouse that have, a cystinotic mice, there is no green protein and there is no gene. And when you look at in a confocal microscope, you see no green cells. The red is just to show the structure of the kidney. But this is what I saw, so I don't know if you can see really well, but this is what I saw when I look at the mice receiving the cells from the GFP transgenic mice. And I don't know if you can, if you can see how much green cells we got in the kidney. It was amazing. It was huge. All the kidney was full of green cells. And this was only 4 months post-transplantation. And I was not even expecting that, it was really very surprising for me. And it has never been published such a success after bone marrow transplant. And this has nothing to do with me. It's just, I think, but it's just because I think, and this is, because cystinosis, I think the bad thing is that all the cells are touched, but it seems the good thing, it seems like there is a strong stimulus that calls the cells to repair them. It seems like, and we have over a project, but try to understand what is the stimulus, because that could be very interesting for other disease, you know. It seems like, at least in the mice, that there is a huge stimulus and the cells are called to, and say, okay, come and repair. And so after 4 months only, we have these huge bone marrow derived cells in the tissue, and in the kidney at least. And I will show you that this is true for the brain. We saw, you know, cells in the brain, so they can migrate in the brain, in the liver, in the muscle, so you don't see well, but this is, they can make myocytes. And now we have also other project, and we know also the mechanism behind all this, but they clearly make myocytes. So and you know that there is myopathy for cystinosis, so this is really important. Or the muscle weakness. I mean, that, because you have to realize that these cells carry the regular gene, so this means that it will be, you know, functional myocytes now. The spleen, I mean, this is where we saw the most bone marrow derived cells, this makes sense, and also in the eye, you know, so even in the eye, we could target the eye also with this transplantation. So it was amazing. I mean, there is a high level of bone marrow derived cells expressing a functional gene, and every single tissue we tested. So that was, you know, for us a huge, you know, results. But you will tell me, okay, that's great, but what about cystine? You know, if it doesn't do anything on cystine, there is no point. So we measure the cystine content in every single tissue, and this was a great surprise. As you can see, these are the mice that receive CTNS minus HSC, so no CTNS gene. And as expected, the cystine continued to increase in every tissue with time, because it's what happened, you know, it increased more and more. But this is the mice that receive cells containing a functional gene, and you can see that the cystine drops with time, you know. And so not only we have a lot of cells in every tissue, but this leads to a decrease of cystine in every single tissue. And I'm not, so this was published in Blood, if you are interested to see the article. And the next question was, okay, but is that last for the lifespan of the mice? And the answer is yes. This, I mean, we tested the mice around 15, 17 months, because usually it's where they start to die, you know, the normal mice, the cystinotic mice, because they're in kidney failure, you know, they're really in bad shape. So I think it was a really good time to test if there were, you know, the difference between the treated and the non-treated mice. And at 15, 17 months, we realized that we still had a huge decrease of cystine in every single tissue. I mean, that goes from 54% in the kidney to 97% in the liver. So this treatment was you know, last for the whole lifespan of the mice. And this makes sense, because once you transplant cells in the bone marrow, the cells stay there, and you know, for all your life. So unless something weird happens, it should be there, and it should last for the life of a patient, you know, if it's, you know, if it would work in a patient. So that was the second good news. But of course, everything is not perfect. So the only tissue where we had, you know, trouble was the kidney, of course. I mean, because it's really weird. It seems like for all the tissue they respond really well, but the kidney was not 100% good, you know. So I will show you. So this is the kidney at you know, 15, 17 months old mice. So wild type look good, you know. This is a normal mice. Cystinotic mice, I mean, you don't need to be a physician or scientist to appreciate the difference, you know. I mean, the tubules are you know, atrophic. I mean, you see that it's not a good kidney. So on the treated mice, sometimes we had mice that look like that. So I mean, this is pretty good, you know, histology. You have some focal anomalies, but you know, the kidney was functional, and the histology was preserved. And some treated mice were like, not better than the non-treated mice. And the question was, why is that? Why sometimes we can treat the kidney and sometimes we can't? And we realized that this one got high level of stem cells expressing a cystinosis gene in their bone marrow. So it was more than 50%. Because when you transplant, sometimes it's not a perfect transplantation, and you have a chimeric population. So you have some host stem cells that are still there, and some cells that you just transplanted. And after it's a balance on, and for the mice that had a good kidney transplant, the balance was like that, more than 50% of their cells were expressing cystinosis gene, so you had few host cells left. But for the other one, it was the contrary, the balance was like that. You had more host cells, so cells that didn't have the cystinosis gene, and few transplanted cells. So the conclusion of that, and this is important for the clinical trial, is that the quantity of stem cells in the bone marrow that express the cystinosis gene matter, at least in the mice. So let's see, because this is only on 15, 17 months left, so I don't know how a human will react, but it seems like it can have an influence on the outcome of the treatment. So we need to keep that in consideration. So the good news, though, it was that no matter what age we transplanted the mice, so I told you the kidney dysfunction starts after around 6 months. Sometimes we treated mice at 9, 10 months old, and we could still get a normal kidney function, at least in their blood and urine. So it seems like the conclusion of that is that maybe we could, the kidney function can be preserved, I think, if it's not too advanced damage, So that's the good news. It seems that even that, what that would mean for patients, it means that we could treat older patients if they still have some kidney function, maybe the rest could, be preserved. But again, this is, just hypothesis. So finally, we showed also that this treatment, so this is a representative picture of histology of non-treated mice, and you can see a lot of cystine crystals. But we showed that even the treated mice that have, few transplanted cells, they have very few or no cystine crystal left. So it seems like the cells that express the cystinosis gene really target the cells that get cystine crystals. So it's really targeting an efficient therapy to remove or dissolve, the cystine crystals. So in summary, so this is the science part. So I will go on more what does it mean clinically for you, but on the science part, this means that at least in the mice, the HSC transplantation leads to an abundant engraftment of cells in every tissue. It leads to a significant decrease of cystine, and this is true for the whole life of the mice. We can have a long-term protection of the kidney, but this depends on the quantity of stem cells expressing the cystinosis gene. And but kidney preservation, doesn't seem to depend on the age of the mice if there is some kidney function left. And we can prevent the formation of cystine crystal or lead to their resolution. So all this, will be very important for any clinical trial we want to develop. So what does that mean clinically? All this, what does that mean clinically for the patient? So you have two options that are presented to us now. I don't know if you see anything, I don't, but you have what we call the allogenic transplantation, bone marrow transplantation, or the autologous bone marrow transplantation. So what is allogenic transplantation? Is that they will use donor bone marrow stem cells to treat a patient, to transplant into a patient. So this would be equivalent to what I just showed you. we use the bone marrow stem cell from another mice to put in a new mice. The autologous transplantation is to use the patient's own stem cells to modify them genetically and to retransplant them. So to be more precise, this is allogeneic transplantation. So the patient goes to hospital. He goes through chemotherapy and radiation to remove their own bone marrow stem cells. And because this is allogeneic, because they use over someone else's stem cells, you know, the chemotherapy is kind of high. And after they infuse the stem cells, you know, just after, but it will be a donor bone marrow stem cells. But because it's someone else's stem cell, and because they have to use a high level of chemotherapy, you have high risk of infection. And if the cells are graft, you have, because it's not their own stem cells, you have a risk of immune rejection of the stem cells. And this can lead to a lot of problems. The good thing of that is that almost 100% of the cells would express a functional gene. And you saw that this can have a huge impact. So there is advantage and disadvantage. But still, you know, this transplantation is kind of risky. So for the long-term run, for for the treatment of cystinosis, we would prefer to go to the autologous transplant, which would consist into harvest the patient's stem cells. You know, as I said, it's just a blood draw. Genetically modify it using a viral vector, and I will show you what virus we will use. Still chemotherapy, but it will be mild chemotherapy because it's the same stem cell, so we don't, there is no risk of immune rejection of them. And after they put, the genetically modified HSC, and the safety of this technique is much higher. You have still, because you use a viral vector, but I'll show you how it works. They goes into the genome, so you have some risk of oncogene of cancer created by if it goes to a wrong gene, it can you can have side effects, and this was seen. I don't know if you heard about the SCID kids in 2003, I think. So the virus they used went to an oncogene, a gene that creates cancer, and out of the 13 patients, I think 2 developed leukemia. But I mean, it was still a huge success because the 13, it was a really bad disease, and it's the bubble kid, they die really prematurely, and they are still, they still live, and they still live normally now with a new with a gene therapy. But still, there were 2 adverse effects, because of the virus vector. But the virus vector they used was a leukemia virus vector. It was derived of a vector that creates leukemia. So now we change the vector, but still, there is some risk. But the procedure per se is much less risky than the allogenic transplantation. So how does a virus vector, how do we genetically modify the cells? So we use what we call a lentivirus. Now for now it's at least the safest virus that we can use. And we got the vector from Donald Cohn, who worked at UCLA, and he already used that in clinical trial for over genetic disease. So the good thing is that this vector we are using is already FDA approved, which is a big deal, if we want to go to clinical trial. So the virus, goes to the cells, infect the cells, and this would be the stem cell. So you imagine your stem cell here. It will go to the cell, deliver the DNA. The DNA will go to the genome, integrate there, and after you can, it will express your protein of interest. So what does that mean for cystinosis? So you have a virus containing Cystinosis. This is your stem cells, hematopoietic stem cells. So I would harvest, not me, but they would harvest, the stem cells from the patient, ex vivo, so in a culture plate, put the virus with it. The DNA, the Cystinosis DNA gene would be delivered. goes into the nucleus, that Cohen explained to you, goes to the genome, and now you would have a new CTNS in all these cells that express a new functional protein, and now your system could leave your lysosome free. And after, when this is done, we wash the cells to remove any virus left. We take the stem cells that will be now genetically modified. Now the virus will be in the genome, and put them back into the patient. And after, we hope that this stem cell will migrate to the organs. And what we showed is, with the GFP gene, this is the lentivirus vector with the GFP gene, still green protein. I don't know if you can see, but we could still make myocytes, kidney cells, hepatocytes. I don't see anything, but so I don't think you see. But the good thing is that we showed that, because you do some ex vivo manipulation of the cell, so the fear is that maybe they won't do the same job. They are not as potent as the normal cells. But we show that it's not true. They still go migrate really efficiently to the tissues, and they have a large plasticity. Make the tissue cells as efficiently as the regular ones. So that was a good thing. We showed also that this was very stable. I don't know if you see, but it's really stable for at least 12 months, and it's where we stopped. But for mouse, it's almost half his life. So it was a stable expression for at least 10 months. So it's stable, and the cells keep their plasticity. And finally, we showed that we could still decrease cystine level with this treatment. And this is what would be equivalent to allogenic transplantation. So all the cells express the CTNS gene. That would be equivalent to autologous transplantation. When you transplant, because the problem is that with this method, not 100% of the cells will be genetically modified. It's not as efficient as that. It will be like between 30–60%. So you don't expect the same efficiency with that as with an allogenic transplant, that's for sure. But we still show that we had a significant decrease, and this was only 4 months post-transplant, so we are doing much longer time point. But at least for 4 months, it was not so bad. We could reduce the cystine level in every tissue, which shows that we are ready. Now we still have to do the safety studies to make sure that everything is fine, but we have the oldest mice are like 8 months, or some of them are a year. So we are really advancing the safety studies, and we didn't see any toxic effect till now in the mice. But this means that it sounds good. We have an FDA-approved virus. We subclone the CTNS, the human CTNS gene, so this means that if we are good and ready to go, we will use exactly the same construct, no need to generate anything else. And we show that it's working. So, that's a good thing. So to summarize the two strategy we want to develop and where we are for this, So for the allogenic transplantation, all the cells express endogenous CTNS gene, so that's the advantage, because I showed that this can have an impact on the results. But you have a risk of immune rejection and a risk of, graft versus host disease. It's after the immune reaction against the cells.
Is it always a sibling?
So I will after talk about what where we are exactly with that now and what the strategy we want to do to try to reduce this risk. The autologous transplant, the advantage is that there is no risk of immune rejection, very few risk of infection. So this is a very I think it's a very safe approach. But you need a virus vector, so there is always the risk that this goes and integrates into a wrong gene. And only a portion of the cells express the CTNS gene. That are the two disadvantages. So what's the next step for the autologous transplantation? So as I said, we are still doing the safety studies in the mice for the the long-term effect of the lentivirus. once this is done, and I think we should start pretty soon the FDA application to request an authorization to be able to use that in patient, but the application only takes 1 to 2 years. And it's where they will have to be convinced that cystinosis really needed. That's why I'm saying we really need the registry, we really need to show that the patients are not cured and need a new treatment. Because they are very tough, it's not easy disease. I mean, we still hear, very cysteamine, they don't need it, so we still hear it. So it's really important that we get more and more patients in the registry. And after we can go to clinical trial. So this will be the long-term strategy. This will be for the young kid. There is no age limitation. But to go there, we need first a proof of concept. So for the FDA to approve it, they need to understand that cystinosis needs a new therapy, but they need to have some kind of proof that this kind of treatment would work in humans. Because when you start to use a viral vector to do any genetic modification, it's where they are more scared. So the first strategy we are trying to develop is the allogenic transplant. To have a proof of concept, and also because some patients will need it now, and can't, because I think the autologous will take at least 3 more years, and some patients will need the treatment now, but also it would be a really good proof of concept, because if we show that this works, I mean, after we would really, they would allow very easily to go to the autologous transplant for all the patients. So for that, for all the clinical trial we want to develop, we have created a consortium, and it's not because it's a great name that we created that. It's because it's really, really necessary. Every single person here has a role in the clinical trial. And you see all their expertise. I mean, Corinne, and she showed you, she's the expert in the gene and all the, the mutation, all the molecular aspect. I mean, Jerry Schneider and Bill Gall will be the one who follow and choose the patients. Don Cohn will be the expert for the lentivirus clinical trial. He's still doing some, so that will be, that's why the first clinical trials will be done in UCLA in collaboration with Don Cohn and Ted Moore, who is the head of the bone marrow transplant department. So right now, it's Ted Moore who is writing, I mean, we are all in collaboration of writing what we call the IRB, Institutional Review Board application, to be authorized to do the first bone marrow transplantation, the allogenic bone marrow transplantation for this disease. And so, as I said, we will do that at UCLA. And the clinical, how do you call that, the criteria to be enrolled in this clinical trial will be to have a healthy HLA matched sibling donor. So, and the patient will have to be more than 18 years old, because it will be it's better, because there is no proof right now that it would work, so they don't want to hear about any kid you get, and so they want 18 years old and more. Kidney transplant, because we want to stop the cysteamine, and if we stop the cysteamine, the kidney is the organ that will be damaged sooner, very quickly. So if they have a kidney transplant, we don't have this risk. They can stop cysteamine, and this won't affect the kidney function. So that will be the criteria, and we need to find funding. But Ted Moore is working on the fact that the insurance should take care of treatment, and the CRF will fund all the extra. Yeah, exactly. So. So the insurance in association with the CRF should be able to cover the first patient for the clinical trial. So where we are is that the IRB was already written. It's a huge protocol. You know, the protocol is big like that. It was done, but they come back to us and saying, because, you know, there is histamine, because it's the first time, because they don't want to take any risk. They wanted us to even reduce the chemotherapy level, you know, to make something milder, to decrease the risk of, you know, infection and stuff like that. You know, because they want to make sure that there will be that the chance of side effect because of this treatment will be low. So, and that's why we also want to use a sibling donor, because, you know, the risk of immune reaction are really decreased.
Yeah, I was just, can you speak to the sibling donor? Are there, what type of, you know, side effects or ramifications, or what?
For the sibling donor?
Yeah.
I don't think there is any, because, you know, they have to go through you know, it's a drug to mobilize the stem cells in the blood. I don't think this has any side effect, and after they do a blood draw of, you know, and I think that's it. I don't think that there is any risk for the donor. Right, doctors?
Yeah, that's true. Also, the good thing, you know, to give a kidney, you need to be at least 18, because there's a long-term implication of that. This is really a short-term, so kids that are 1 year old can do bone marrow donors.
Does it matter if the sibling's a carrier?
Yeah, it doesn't matter. Because I did the proof of concept in the mice, I used heterozygote, so carrier, and this works perfectly well.
What would a transplanted kidney, how would that be affected if you're doing the chemotherapy to get the patient ready for the stem cell transplant?
So that's a very, very good question. So you have to know that the chemotherapy has some effect on the kidney. So that can be toxic to the kidney. So that's why we need to have a good kidney function when this starts. We can't afford to have a patient who had a kidney transplant and not a good renal function. If the kidney function is good, I think it will be fine. You know, the risks are minimal. But we can't afford to have a bad kidney function at that point, because there is a toxic effect on the kidney.
So what's your ETA?
I just want to what?
What's your
When do you think you'll have your first sibling?
So what will happen is that, so Ted Moore is correcting the protocol right now to make a less toxic chemotherapy, and I'm hoping within a month we will be able to submit the IRB, and we should hear within a month the feedback, at least, because they can come back a month after we submit it and say, we don't want to take the risk, go somewhere else in another institute, because it will be UCLA's risk, and they will say, no, we don't want to take the risk, the patient can live with histamine, we don't want to even try it. Or they can come back to us and say, okay, we like it, we okay to do it, but you have to modify this, like they asked to modify the chemotherapy. They say, you can modify this or that, And
you're using HIV? Is that
yes, this is a really good one. I didn't even say that, but yeah, it was. So the virus that we are using, it's HIV-derived virus. And this is a great virus, I mean, not for the disease, but what the people did, and I have nothing to do with that. They are, specialized people who are very good to design the virus. So what they did is that they removed all the bad gene of the virus, the gene that makes you sick. But they kept the capability of the virus to infect the cells and integrate into the genome. So they kept their good ability of infecting the cells, but they removed the bad gene that could get you sick. And what you have to understand is that now there are clinical trials that are more than 3 years that use this virus vector in kids, and no side effect has been seen till now. But again, it doesn't mean that it can happen. But it's with time, with the experience, that we know if it's really safe or not. And it seems like till now there is no adverse effect that has been seen with the antivirus vector.
Okay, one more question.
So, Dr. Cherqui, outside of us, the people in this room, or our collective little network of people within Cystinosis, of course you want us to sign up for the registry. Funding, we would do collectively what we could to help out. what else would you ask of the people in this room, selfishly, in your position as the doctor who's potentially saving our kids? You know, what could we do to help you out?
No, I think I have to say, and it's a good opportunity for me to thank the CRF and and all you guys, is because this project would have never been started without them. I mean, I was a young investigator with this idea, and believe me, no governmental funding would have even bet on it. So this was great. They gave me the funding to be able to start this project. Now I think we are in a good position that we did the proof of concept. The governmental funding, the NIH, fund me now. So I am in a great position. Selfishly, I don't need to ask anything else. I think you guys did a great, and thank you for that. And what is important is, again, to register, to be one big group behind in one foundation. I think everybody needs to be together in this. We will need everybody together and not apart, and that will be very important. And when the call will be made for the recruitment, is that two people respond as soon as they can, and play the game.